Okay, we're all back here. So let's get back to the pile foundations again. But this time we're looking at piles in laterally spreading soils, and we're worried about the horizontal or lateral behavior of these piles. Like in the morning, I thought I'll start by looking at what people have done and what methods are there, and how this problem has actually evolved over the years. We talked a little bit about the PY analysis yesterday of how you can have these lateral springs. So if I can remind you, so PY analysis basically involves having lots of springs in the horizontal direction. It's used for horizontally loaded piles, originally developed. Like that. So the soil pressure acting on the pile is P, and Y is the relative displacement between the pile and the soil. One of the early attempts of looking at this pile soil interaction during earthquake loading was carried out by this guy called Merson Weirschon. He's clearly Danish or Dutch by origin. Uh, his PY spring was very simple. Uh, he basically said, we'll take this reaction force acting on the pile to be linear up to a point, and then stays constant beyond that. So it's like a bilinear fit. And so you got the reaction force P, relative displacement Y, and a limiting pressure. This limiting pressure does make some sense, because if I'm trying to push my pile in and the soil has to flow around it, the soil is obviously going to be limited by some ultimate state it can reach, which will be its passive limit. Beyond that, it will simply fail, form a wedge, and the rest of the soil will flow around it. So this is okay, although it is on the simple side, because it is, he's saying you reach ultimate state and that's it. And you're linear up to that point, you're linear after that, and it flattens out. Based on this, he the most important contribution I believe is done is he linked the axial load on the piles, which is obviously what we are interested in, to unstable and stable states. Buckling, as you know, and we have done this enough now, is an unstable state. It's an instability. So that's one zone where very high axial load, you will enter that particular region here. Now, if your pile stiffness is low, obviously you have more chance of buckling. And similarly, if your soil stiffness is increasing, then the pile is more likely to die quickly. This is what we want to, this bit is also straightforward. This is simply bending failure. That is, I apply more horizontal load, the pile effectively bends more and more and more until plastic is formed. He also identifies this other region here called the soil flow. This is where for laterally spreading soils, they start to add to your failure criteria. So this was back in the 1994. Then there's this guy, I've forgotten his first name, Go. He's the professor at NUS now, and Tom O'Rourke. They came up with this concept of having not such simple, go up, stay constant PY curve, but slightly more sophisticated. Let's spend a little time looking at this. So they first separated out the smooth and rough piles. And now that is important because our steel piles, you normally consider them to be quite smooth. Concrete piles, probably on the rough side. You sometimes put coatings on piles to make them rough and to protect them in other ways. So you want to know that's a parameter. So they considered those two to be separate. The nice thing they have done is normalize the force. The horizontal force is divided by, I'll write this down, P over SUD. This is always good because it non-dimensionalizes the load factor. So you can compare one with the other quite nicely. Because we are applying these now as a limit states, you can also carry out upper bound, lower bound solutions, which Randolph and Holsby have done long time ago. So they're not. So this is the worst case you can get. So this is like a combination of upper and lower bounds, which means those are the true collapse loads. And you can see for the smooth pile, they got something like about 9. And that makes sense because if I look at this pile in plan view, it's like the soil is flowing like that. And for this, we can get the upper bound. And that is going to be same as, so if I take a pile trying to be pushed in, the soil flowing along it. And we know this mechanism for that, the deep flow mechanism, and that is again 9, right? Roughly 9. So this sits well with the known theory for piles going this way to soil going that way. So 9 is a good reference point there. But if it is rough, it can be as high as 12. Now the good thing is, if you have done your site investigation, you would know your CU or SU, and you know the diameter of your pile. So I can say, if my displacement of my pile top is going to be, say, 100 millimeters, then I can normalize that with my pile diameter. So I would know where I am here, maybe 0.05 or something like that. And then I can go up and read that and say, for that I'm going to get 7. So this value will be 7. And then I can work out what my P should be because I know this and I know that. Mind you, this is all assuming that there is no dynamics involved. This is just the pile and the springs, and we're only doing equilibrium calculations, if you like. But it does a lot of things right. There's only one little thing. We upset Tom O'Rourke when he showed up on sabbatical at Cambridge with this paper waving in front of us. And it took Stuart about 10 minutes to find the fault with it. I'll come to that in a little while. But I'm a great supporter of simple things like this. because it gives you the framework and it's something you can use readily without too much uh, wrong with it. The other nice thing about this particular piece of work is that they took the data from RPI centrifuge test and checked that well, they fitted this to that data. Okay, so they got a bunch of experimental data of piles in liquefiable soils and said this curve fits them nicely. The In order to make it fit, obviously they have used this kind of simple, if you like, constitutive behavior, which is they're plotting plastic deviated strain on the x-axis. This is basically how much is my irrecoverable strain happening. As the soil wants to move past the pile, it is going to suffer irrecoverable plastic strains. So if I have a measure of that, and I know what my initial undrained shear strength is, then they're saying up to about a plastic shear strain of 0.02, there's a linear drop. After that, it remains at its minimum value. And we can argue about these limits of the variation style, but broadly we know the undrained shear strength should drop off with accumulation of strain. No doubt about it. We know you're breaking up the soil, so it has to get weaker. Now I come to the problem part of this. The problem part of this is this type of model is only characterized by, well, it's characterized by 4 points. One is what is the peak level you can get to, the slope of that initial slope, what is the falling leg slope, and what is the residual. So those are the 4 control points, the 4 variables or 4 parameters for you to choose. But the equation actually has only 3 unknowns. Okay, so I have 4 variables and 3 unknowns. So it's over constrained, which means you can give me any data in the world, I can make it fit by choosing those 4 numbers. It's just over constrained. I believe Go pulled a fast one on Tom's work, and Tom did not realize this when they published it. That does not mean the framework is wrong. That does not mean that the work is not valuable. It's very valuable. However, mathematically, it is not sound because you should never over-constrain a model. If you over-constrain it, you can fit anything you like. The fact that it fits the centrifuge data well is a good example of that. But even if I gave him some gobbledygook, as we call it, it will still fit it. I can still choose those 4 numbers and make it fit. So that's the downside of it. But okay, everybody makes the odd mistake, I guess. Then we also have another idea coming from Liu and Dobry. These are all classical papers. You should read if you're working in this area with some interest. Who knows? You might find even more flaws than we found, which is how it should be. Now, these guys said, right, I mean, these are centrifuge people. This is the RPI data the other guys used as well. But they came up with this concept that let's look at the increase in pore pressure as a percentage. So 0 to 100%. What they call this coefficient Cu is, I'm sorry, I'm flicking between SU and CU. I'm just following what the others did. But be rest assured, they mean exactly the same thing. It's the undrained strength. And because they consider liquefaction all to be undrained, an undrained event, they'll always work with Cu as a strength parameter. So Cu naught is the initial before earthquake strength. Then, then what they're plotting there is the current Cu over Cu as a ratio. So the before any pore pressure is generated, obviously these two will be the same. Therefore, it must be 1. And when it's fully liquefied, this becomes 0. So you should come down to 0. So the ends are fixed. So it makes sense that it should come to 100 here and should be 1 at it should be 0 at 100 and 1 at 0. Those are easy. We can logically see that. Now the question is, how does it change in between? And they propose this parabolic fit, and all these dots are their centrifuge test data. It seems to reasonably follow that. So one way we can say is, instead of worrying about this type of curve, you could say, if I know my pore pressure or expect a certain amount of pore pressure, 3/4, half, whatever your choice is, 50%, 75%, then you can reduce your undrained strength by this factor. So I go up here, say at 80%, I'll get a 30% 70% drop off in my initial strength. So if I know that, then I can use that to see how much more my soil will move and how much more it will be acting on the car. So this is another way of doing it. Again, this is based on experiment, so we've got to take it seriously. Now, we had our own go at piles in soils, laterally spreading soils, and we started simple. We started with single pile. So, but our tests are a little bit, we feel, more sophisticated because we measure the pore water pressure next to the piles, both upslope and downslope. And we also try to measure the stresses, contact stresses, and measure the strain gauge, bending moments through strain gauges, and back out from those the soil pressures. And then the main reason we did this was at the time we were doing this research was when the big Kobe earthquake has happened, and a lot of liquefaction happened and a lot of lateral spreading happened. And the Japanese were using what they call the JRA code, which is Japanese Railway Authority, I think. They came out with this guidelines of how do you work out soil pressures due to liquefaction. What do you do with the non-liquefiable crust? What do you do with the liquefied soil flowing around your farm? So we wanted to see how good those recommendations were. So we started simple, as I said. We had a dense sand. In those days, we could not tilt the box, so we had to create a dense sand layer to give us the slope, and our loose sand, and stick 2 piles, one square and one circular. I briefly mentioned this yesterday also. And we were putting fairly large number of cycles because we want to get as much spread as we could. One other feature I forgot to mention is this was a time where I felt it was important that we model the seepage right in the slope. So we were maintaining the water level there and there at the ends of the box to a given level. So we had peristatic pumps pumping fluid back up here in front so that the flow can continue and we got a steady seepage parallel to the slope, which is a condition not often done in many other experiments. So then once we have a steady seepage, you shake it using this particular input motion. This is from good old days, my SAM actuator. So it could give you any number of cycles at any G level you want. It's as long as you want sine waves, it's happy. So we did this. And the peak accelerations of this were about 2 meters prototype scale. So that's like 2 over 10.2 G. Okay, so plus minus 0.2 G to begin with, but afterwards it's steady, it's down to about 0.1 G. The design of piles I want to just focus because some of you are coming and talking to me and saying you're going to do experiments. There are a few tricks you can do. So here we wanted piles of different cross sections and different areas so that we can attract more or less of the lateral load from it. But if we made individual piles, it would cost me an arm and a leg to just buy the strain gauges. Because every time they need to be strain gauged, although the gauges are about 20 pounds each, the labor to get them fixed by for an electronic technician, you've got to see at about in UK about 800, 900 pounds per pile. So I wasn't prepared to spend. I can spend once, but not 10 or 15 times. So Stuart came up with this idea that he's not going to gauge the pile, but he'll gauge 2 strips, 2 metal strips. And we have the metal strip inside and make a foam pile outside. So the stiffness is all coming from the metal, but the force is all being attracted by the foam. Okay. Initially, we weren't sure how well these work, but they worked beautifully. So I'm quite pleased with this idea. Nowadays, I got a bit more research funding, so I don't need to cheap out like this anymore. So we're getting more piles gauged, but it's a good concept. Anybody can use it. And they all go into the base and are basically glued together there at the base of the alloy. So that's the detail of the pile, and this is the model. So I'm going to forget all the other instruments, but the pore pressure transducers upslope. So the slope wants to go this way, so I'm going to call these 2 upslope, these 2 downslope. And the key thing, and the slope angle is about 6 degrees, so it's not that steep. So the key thing we did compared to any other people before us is actually get these measurements so close to the pile. And it turns out that is the key. So let me show you the measurements we made. So upslope and downslope at shallow depth, which are these two guys, and 3.5 meters below surface are these two. So upslope ones seem to produce about 20 or 40 kPa depending on the depth. Very strong dilation there, and but it dies down quickly. Downslope is unexpectedly showing more dilation for much longer and strong dilation as well. Why is this? The pile is there, the soil is trying to flow past it. The downslope is the one which is getting stronger and stronger, and it took us a little bit of this by surprise initially when you look at the result. So when you change the stiffness of the pile, so we tested flexible piles and rigid piles with the same idea. You can see the difference is even more clearly. Like for flexible piles, okay, the pile is able to wobble about a bit, so you will get these suctions coming up, which die down upslope. And for rigid pile, these are much smaller. And only when the soil starts to move past the rigid pile, you're getting some oscillations. Whereas downslope, for the flexible piles, it's even going into absolute suction here and down here. And rigid piles also, it's very comparable. So something is happening downslope of the pile, which is quite important, which nobody would think of, because you'd expect, okay, if the piles are here and the slope is moving this way, I'm always focused on this part because I'm thinking, oh, my soil is coming towards my pile. It's all going to be mobilizing lots of passive pressure, but you won't worry about the other side of the pile. Well, that soil can just flow away. Who cares, right? But it's according to this, no, you need to pay more attention to that soil. It's doing something interesting. So we said, how can we look at this? So you could look at the difference between the two. In effect, what the pile cares is the difference. So if there is any phase difference between upslope and downslope, yeah, then your difference gets added up, and it does. So you can see big oscillations at shallow depth and also at the greater depth. And we're calling it a hydrodynamic force because effectively you are looking at the difference between the two. And for rigid piles, also, firstly, the pattern changes, but the sizes are bigger. You'd expect them to be bigger for a rigid pile because it's not going anywhere. It'll attract more force. That's a given. So now the axis go up to 40 kPa here. Now, so we know the vertical stress, we know the core pressure. Vertical stress is because we know the weight of the soil, total vertical stress. We know the core pressure, so we can work out the effective stress. We can also look at the changes in total stress. So if you do that, again, looking upslope and downslope for the rigid and flexible piles, you get this picture of buildup of these total stress, upslope, and a drop in total stress downslope. And the same thing is happening with the at a deeper level. That in itself does not tell us, okay, you know the changes are happening. What you want is to look at the ratio of the vertical stress to horizontal stress, or how does that change? Because that tells you the earth pressure coefficient, if you like. You all know Ka and Kp, active and passive earth pressure. So which must be the bounds on this variation. So if you now use the stress information and the core pressure information to plot vertical effective stress and horizontal effective stress, then you see that what's going on quite clearly. So let's focus between upslope and downslope at a 2 meter depth. So most of the time, the soil is, if I plot the stress bar, is spending time close to being Kp, which you would expect, right? Because the pile is there, the soil is moving down there, so it must be close to passive, and it is. On the other side, downslope side, I would expect most of the time it to be at Ka, but it is not. It starts nicely there, but as the cycles progress, it's trying to get more towards here. That's because it's all coming because of those big suctions we are seeing. The big suction that is developing on the downslope side is pulling on the pile. And that's why it's trying to take it towards KP. And that's why we got all this extra behavior. So if you don't do this plot, I could be looking at those time traces until cows come home, and I wouldn't know what's going on. So it's important when you get the data to try and look at it in different ways, especially in ways which you can easily understand, like active and passive earth pressures in this case. 3.5 meter depth, same idea. So upslope more or less, but of course it does not need to be at KP all the time because there's less movement deeper. I was drawing earlier, my displacement is like this. So I'll get more displacement of the soil at the top than at the base. As I go deeper into the ground, it moves less. Therefore, I'll only need to be at the KP limit for some of the time. And downslope, again, it starts at active, but this time it's almost coming very close to KP. It's in fact mobilizing the full passive pressure for some of the time. So the pile is not only being sucked downslope at the top, but even at the base, it's being asked to go towards passive state. This is completely different, real, and reassuring. That okay, soil does obey these active and passive states.
Sir,
Why is
the
it crossing?
the pile is going to move more at the top. As we seen earlier,
Yeah.
pile is going to move the top, maximum at the top and less at the base.
Yeah.
So since there is more movement, there should be more force in the top itself.
Yeah, we're not talking about forces here. These are stresses trying to pull on the pile, which will be proportional to the suction it seeks. So if I get the suction, this will say I got more stress. So we're only looking at stresses, right? We're not linking this to strains yet. So it is right. I haven't done any manipulation. I just plotted the same data for both. All I'm saying is, look, this even downslope, there is part of it close to KP, which has to be true. It's not in contradiction with the fact that more soil moves on the top. More soil moves, no, soil moves more on the top. That is true. But when you're looking at stresses, the deeper one, even though it may move less, it is under higher stress. Therefore, it can get more suction and therefore can apply more force onto your pile, which will all be reflected in your bedding. Okay? So that's more flexible pile. Rigid piles, less so, in the sense that at the top, clearly KP, no question. Because pile is not going anywhere, soil is coming, clearly KP. This one, downslope at the same, oh, I got this labels wrong. That should be 2 meters and this is 3.5. They're exactly the same experimental setup. The labeling is wrong. It's doing something similar to the flexible one. Here again, at depth, you got the things sitting at KP, but at deeper depth, you got a big variation going all the way from Ka to KP as you cycle and cycle and cycle. Because you're kind of creating some confusion in soil's mind. Because I've got my rigid pile at depth, the movement of the soil is less. So, but on the upslope side, it can get to the KP, no problem. On the downslope side, it does not have to go that far backwards to create passive pressure. So on my upslope movement, I'll hit KP, but on my downslope movement, I'll get to KA. This is why when a pile is rigid and the movements I require of my slope is small, and oscillate quite wildly between K and Kp, which again makes sense. Now, as I said, we tested these shape effects, if you like. Because my original idea for this PhD research is I was thinking that why can't we streamline parts? Why to avoid this lateral load from a liquefied soil? that was so we kind of looked at the bending moments in the circular and square piles at different depths. Okay, that's just the data showing. So we got at 3 locations reasonable bending moment time traces, and they look different for circular and square pulse. Square pulse is picking up more quickly than this. This is more gentle, and otherwise very similar. Boring. But that's not the purpose of the measuring the bending moment. The purpose was to compare what the JRA code says, the Japanese code says, in estimating the lateral pressure exerted by the liquefied soil, which is what we got the measurement for now. They claim, okay, the Kp in non-liquefied crust is whatever it is, but there's a 30% of total vertical stress must be applied on the piles horizontally. Only 30%. So we plotted the data. So we got our bending moment, as I showed you before, at different depths. And we plotted, so that is for square pile, that's for circular pile. Circular pile is giving slightly less bending moment, as you'd expect, because the flow is more smooth. But nothing to write home about, as I thought it would be. However, this is what the Japanese railway is designing for. Clearly, a lot less than what we were measuring. The reason they were doing that is nobody understood what the soil on the downslope side is doing. And the bending moments are jumping up to be big for us because of the suction measurement we were having in the soil next to the pile downslope. Okay? So, at depth, the error, if that is about, say, 70, and we are at about 150, that's nearly a factor of 2.2, 2.3. What did we say at the beginning? For static design, you'd consider a factor of safety of about 2, 2.5 for piles. So it's going to fail. No wonder so many bridges, pile foundations in Japan have failed. Because JRA was considered to be the best, most up-to-date code following Kobe earthquake. Now they have revised their code following now. It's a lot more. They basically multiplied all their factors by a factor of 2.5, almost directly from this graph. Uh, and it's interesting. You can also plot where the JRA code non-liquefiable crust calculation, and then they're dropping that quite down to, because the rule is 30% of total vertical stress, as I said before, and these are all our data points. So we are measuring net horizontal stress of 60, 70 kPa, while they're predicting 10, 15 kPa. Okay? So that's a neat story where lateral spreading studied from for very different reason suddenly throws up things you don't expect, and that's why you do the experiments in the first place. If I know everything about how the experiment is going to behave, there's no point doing it. And that's why it's fun. Just to capture those points, the soil dilation close to pile causes large transient loading being applied to the piles, and particularly coming from the downslope side. Obviously, pile flexibility reduces the loading attracted to the pile. The more flexible it is, the less load it will attract, and but you will pay the price in the form of displacement. The stiffer you make, or the more rigid you make the pile, the less it moves, but you pay the price with extra lateral load. So it's one half a dozen of one or six of the other. We kind of got disappointed a little bit and put this comment here. Square and circular piles suffer similar loading, which is slightly lower for circular pile, but not really, as I hoped, big difference. So there's not much mileage in it. There were some interesting features as I was explaining the other day. How much soil gets involved for square and circular piles, but that's another story. We're not going to go into that. Let's stay focused on it. The JRA code under predicts both the peak bending moment and peak stresses on the pile, and this is especially during the earthquake loading. It's not so bad if you're only worried about the transient loading, the residual loading after the earthquake has finished. But who cares by the time your bridge is collapsed? But as I said, they did update their code now. They got JRA 2006 or something now. So, any questions on that part? We looked at just single pile, looking at lateral spread, and got some interesting stuff to talk about. And we also looked at the simple ways of these PY springs and what type of relations you can do. Depending on how much time you want to invest in it, you can go from simple bilinear PY curves to a little bit more sophisticated ones. So shall I finish this and then we'll have time for discussion, yeah? So, I've been showing this yesterday, especially the left one, where you kind of went and solved this problem also at home. Looking at the liquefied sand and rock socket, and that is forcing the thing to undergo these kind of pin mechanisms, plastic pin mechanisms. But more realistic case would be something like this, where I got a non-liquefiable layer on the top, which wants to go down slow. I got a liquefied sand that wants to go down slow, and I got this dense sand which is not going to go anywhere. And the piles typically go through that. You got pile cap, which is a bit embedded. Once it's embedded and the crust wants to go, if the pile does not want to go as much as that, again, the pile cap will attract quite a bit of lateral load as well. And because this is strong soil, it's going to mobilize quite a lot of passive pressure. It's not like liquefied soil just trying to go past your structure. So these are all important, realistic variations you need to consider compared to something we drawn on the back of an envelope. This is a nice simple experiment, but this is a bit more complicated. Now, let's have a go at looking at the. I want to get the maths out of the way first. I don't like maths, but you need to do some maths, otherwise. So what I'm trying to focus on is pile, one pile cap, vertical load, and some horizontal loads. Okay, that's what these are. So if the figure is clear enough, then I don't need to redraw it here. But if not, I will. So we are saying that let's start with the pile bit. Maybe it's better if I. So if I take the pile only for the case I have shown, this is going to see all this pressure on it from the liquefied soil trying to flow past. Yeah. Let's say that the liquefied soil is going to apply a pressure of PL and the diameter of the pile is D. So PL times D gives me the uniformly distributed load equivalent. Pressure times diameter must be kilonewton per meter, right? So that should be like a UDL on the pile inside. What else does it have? It has axial load. Let me call it big P. And the frictional stiffness is EI, but we're only looking at the forces. It will have, because I need to maintain horizontal equilibrium, so clearly I need two horizontal forces. I'm going to call this A and that's B. So I'll have a FA and FB. Will this be in equilibrium now? What else is missing? Moment. Right? So we need to apply MB and then MK. Okay? So if I just take this bit and say I know all of those, I can write expressions for my bending moment, moments at A and B, and the forces FA and FB, which are as shown. So if I'm allowing a deflection delta, this is where the buckling thing is coming in. So the P delta is the extra moment I'm going to generate because my pile is going off center line. Yeah. And using this factor F delta and FPL, we'll keep them to one side. These are like scaling factors, non-dimensional factors. Keep them to one side. Let's say we know them, and I'll come to that in a minute. But once I put that in, the rest is simply writing the equilibrium equations. Also, for sake of keeping the equation legible, we are defining this mu, which is like Euler's buckle, if you like, modified version of it. Pure So we have this expression for MA P delta F delta minus PLD or U squared FL, FPL. And similarly for FB, for MB, it's the sign goes plus P delta F delta minus PLD, exactly the same as that. Using those two, if I know the moments, I can write the force equations. By the way, you can check these if you want. Now LEQ I'm taking as the length of this file, but if you want, you can adjust that using your engineering sense. If you feel that the pile is going to bend more if it's not quite rock socketed here, or if you got more length into dense sand, you can adjust the effective length. We kind of looked at that before, how to work out effective lengths of a pile and flexibility of pile are covered separately. But you can use that. At least we can, the simplest thing would be to say the equivalent length is the liquefiable thickness. So that is LEQ. NB minus MA plus the loading due to UDL minus P delta will give you FA, and FB will be simply minus FA plus the horizontal load, because sigma H must be 0. That is just for the pile. What about pile cap, which is sitting in the non-liquefiable crust? If it is sitting in a non-liquefiable crust, and I draw the free body diagram for that, I'm going to get the forces on the pile cap are my n times p, because n is the number of piles, will be my total vertical load, and the pile I'm considering will give me p. These are okay, but the F thrust, or the horizontal force due to the crust, is the big one, really. So that you can estimate if you know elastic modulus of soil. I hate this part. The K is like a spring constant for the non-liquefiable crust, and that times the relative displacement of the between the cap and the soil, which is how much does the crust move and how much does the pile move, pile tip move. If you subtract one from the other, you'll get the relative displacement. So that should be the force acting on the cap. So we can solve these equations without bothering about anything else, provided we know some the pressure applied by the liquefiable soil. Okay. So this type of analysis obviously is called a limit equilibrium analysis, because you are only considering this once the soil has liquefied and everything is in a quasi steady state. Now, I left this. We left these two hanging out there. Let me address that. So, if I know my mu value, and if I multiply that with L, and I plot that along the x-axis, the factors F delta and FPL, you can use these curves. Okay, so you can simply pick the value of F delta and FPL depending on what your mu L is. So, in a way, these are the non-dimensionalized factors you're incorporating into your limit equilibrium calculations to handle the uncertainty in terms of what PL is. So this gives me a way of doing my centrifuge test or borrowing data from other centrifuge tests and say, right, I'm going to make these curves basically take that experimental evidence into account. So you don't need to do experiments every time you need to design a pile group, which is foolish. Okay, so that's where those two factors are coming from. So we've drawn these based on the experimental results we got, so that you don't have to. Right. So that is the simplest limit equilibrium calculation you can do, and people have been doing something similar. For example, Dobry and Abdul have a similar set, but they don't consider the P delta effect. Our thing is that we should consider the axial load of the pile as well. Otherwise, I'll show you some evidence why this is important later on. Because most of the experimental work before this happened with just piles and pile cap, very lightly loaded pile cap. Nobody was worrying or considering the fact that the pile cap is there to actually carry some vertical load. People ignore the structure, and that's a problem. problem in the sense that it affects how the pile group works. It's not that we are so enamored with the structure on the top, but if it's going to make a difference to how the pile foundations are behaving, we need to know that. Right. It's also possible to extend this concept a bit into including some inelastic effects. For example, I can adjust the difference in the movement of the crustal soil or the non-liquefiable crust on the top compared to the liquefiable soil. I said that it's possible that the crust can move more compared to the liquefiable soil because this water film can form and the block can slide down. If that is the case, we can handle that by simply increasing the crustal soil displacement. So that will increase your force because your relative displacement between the crust and the pile cap is increasing. That will basically jack up your force and may lead to structural failure before the soil heals, just because the crust wants to go a lot longer. Also, uh, if you combine that with weak crust compared to strong crust, then you could yield the soil, not make the structure suffer. Both those extra things you can handle by changing where you draw your soil yield relative to structural yield lines. So some inelasticity can be, some inelastic effects can be included. So if you take one more minute on this, what we're saying is if I can draw the plan view, say that's the file cap. These are the files, right? And we are sitting in a big crust which is trying to move that way. if the if the crust is very strong, let's say has 100 kPa C, what is likely is that the force it can apply on this is so big, it will probably cause the structure, when I say structure, the joint between the pile cap and the piles to shear off. In which case, we'll call it a structural failure, nothing to do with us. Right? However, you say this is 20 kPa, then you can very well imagine the soil is trying to flow that way. I'll get my bearing capacity failure. Yeah. So this should, from upper bound, I know the answer to this is 5.14 cu. So if I'm applying 20 times 5, so I'll get a horizontal pressure on this of 100 kPa. Easy. And if I multiply with the face area, I know the horizontal force. I don't even need to work out the stiffness of the soil. I'd rather do this. Easy. So if it is soil is weak and we know it fails, this is easy. If it is structural failure you're expecting, then what you'll do, you'll say, right, you'll do the similar calculation. Your horizontal force will come enormous. You'll work out the shear capacity in each of your piles and see whether the shear capacity is there or not. And you'll find it isn't there, therefore that's where it's going to fail. Yeah? So that's just design decisions you can make. All coming from fairly robust and simple thinking. Now we can make using no more sophistication than what I have explained, compare what a single pile does compared to a pile group. I'm not saying we consider the uh, in, the complexity of soil flowing in between the piles. We're just saying this single pile, I can do this calculation. I got pile group, I can do a frame type calculation of that and compare one to the other. So what this says is, okay, I got this non-liquefiable crust on the top. So that is single pile. So my bending moments are shown here along with the deflection I'm getting there. And this is slightly how the bending moments are changing with depth. So I'll get big things there on the positive, on the negative side, and the positive bending of the interface between liquefiable and bearing layer. This is more conventional. We understand this more easily. So the more deflection I'm allowing the pile to undergo, the more bending moment I get because my curvature increases. Pile groups are slightly more tricky. I mean, first of all, this is almost a linear increase with deflection, which kind of makes sense. If you've got enough piles to make a frame, the more deflection I give, the more movement I get, and that's just a linear relationship. Whereas the variation in the piles with depth is slightly, it follows a similar trend, but you can see the magnitudes are quite different. And that's because when I have, I'm asking a pile group to bend, you will have the uh, front piles and the back piles helping you to take the moment. Okay, which means the bending moment in the pile itself need not be that big because you got the frame action helping you. It's like applying a reverse moment at the end of a beam, a fixing moment at the end of a beam. So you can do these kind of nice calculations. Now let's see how all this actually pairs up when we put the data on the. This must be an old slide. It says that our paper is under review. No, it's been published for 10 years now. So about that, I did update the slide. So we did the pile group test. Now with the proper axial load, and I'll come to that in a second, and sloping ground and non-liquefiable crust. So everything put together of what we are talking about all morning. So the blue bit is the non-liquefiable clay crust. You've got the loose sand, dense sand, piles going about 7 diameters into the, 8 diameters into the bearing layer. So they've got enough embedment. And the whole container is sloping at 6 degrees, I believe. Yeah, 6 degrees slope. And you shake it. Now, two different combinations were tried. One is when the axial loads are fairly light. So you only have, so this is axial load per pile. So you're talking about 345 kilonewtons prototype. Or another heavily loaded case where you got 1,000 and 1,100, 1,155 kilonewtons per pile. In both cases, we're applying comparable accelerations in that one is 0.2, one is 0.26, slightly bigger, but above 0.1 G, we know the ground liquefies. So that's irrelevant, really. But the important thing is, got two differently loaded, axially loaded piles. So, here what you're seeing is the horizontal load versus the horizontal deflection of the at the top of the pile. What obviously this is like the video I have shown you. You have the cycles going on, and it'll accumulate and goes. So the fact that I'm doing cycle, 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 and when I go horizontally makes sense, which is we have seen this yesterday already. But the cool thing is you can take the cyclic, you can filter out the actual earthquake cycles and get the underlying monotonic response just by removing the cyclic components by filtering. So this kind of tells us what is building up in the pipe, because this is being continuously pushed in that direction. So yes, overall it is doing that, but inside that it's only going one way, down slope. So the dynamic component, as you can see here, is quite large. It's almost 1500 kilonewtons, whereas this underlying static component it only gets up to about 400 kilonewtons. This is when the pile is likelihood. Make the pile carry a lot more load axially. Look at these ones. The dynamic component is going crazy. It's going up to, oscillating both sides wildly, going forward, coming back, going forward. The loops are what's going on here. And however, the residual ones are more or less, actually, they're smaller than this one. So this is the first time anyone has looked at applying while the pile is actually carrying the load. If you have this non-liquefiable crust pushing on it and the soil liquefying, what exactly happens? And apparently it's quite different and dependent on how much axial load the piles are carrying. The behavior is very different in the two cases. So, okay, I'll come back to that in a second. So let's just see physically if this makes sense. So I got a pile which is lightly loaded, in fact a pile group, but each pile is lightly loaded, and I'm trying to get it to shake this way, and it says, right, I only need to go down slope. I need not come back up again because my load hasn't got all that much inertia to push me back. That inertial component of the mass sitting on the top is not big enough for it to push the thing back up. Whereas when I have much heavier load, the inertial component of that mass means I can oscillate a lot more vigorously, and therefore these loops are more both to positive and negative side. Make sense? Also, the accumulated displacements for the same earthquake, these are getting up to that stops more or less at a meter. This is a bit more. So although the residual component is kind of smaller in terms of load, you are going further to one side at the end of it all, which means this is the effect of the P delta. All these intricacies are captured by this. The reason these are funny shaped like that is because we made them fit that data. Okay? So, but if you don't know this, you will always wonder why the heck did these guys draw these curves in this arbitrary fashion? It's because you need to know the background. But it's worth admiring this for a while. It's complicated stuff. But there's so much more can be done. For example, what happens if we push this load even further, closer to Euler loads? You know, but another way to explain this story is by plotting the traditional H versus horizontal force versus horizontal displacement plot and see why in some cases you get buckling and in other cases you don't. So one way you can look at it is to say for the lightly loaded case, the blue line, so that's typical yield and ductile behavior, right? So you go up linearly up to yield and you have elastically up to yield and you deform in a ductile fashion after that, which is considered to be stable from a structural design point of view. In fact, you can work out your ductility factor depending on how big it is. The black line, which is coming from the experiment, seems to more or less do that with some minor kicks up and down. Now, if I load my pile heavily, I go up and follow a similar concept, I'll get to a point where it seems to fail. The reason is if I plot my black line, which is the experiment, it comes there and has a negative slope. So when I encounter negative slope in this type of plots, that means the system will run away to failure, which is what we call instability or buckling in previous classes. So the fact that my experimental line went up to there, stayed a bit constant, and then trying to go down the slope is not good. That means I'm going to accumulate a large displacement, horizontal displacement, with a dropping horizontal load. That's deadly. That means you're not going to recover from that. Your pile group is bye-bye. It's dead. So this kind of plastic yielding and collapse are well explained and captured by the experiments, and they're telling us the axial loads can make you jump from being this to this. So the more heavily you load your piles, the more you are pushing it towards the red line from being a nice blue line. Now that's worth a lot, isn't it? To know that. What is the effect of axial load? You can think of it in another way. The material can only carry a certain amount of stress, right? You normally work out your principal stresses and work out how close they are to the yield using one criteria or the other. Stress curve, pick your favorite. What we're saying in our case for piles is this combination of axial loads and horizontal loads are basically eating up into the capacity of the pile. And the more you put on in terms of axial load, it can do less in terms of the horizontal resistance. You can't have it both because the material can only do so much. So this is that's a simpler way of explaining it, but this kind of tells you which particular how much this is quantitative. You can actually work this out. You can plot these graphs and see where you fall, and then work out exactly what capacity you got. So from a design point of view, you really need charts like this. Last one, I promise, is once you understand all of that, you can make more design charts like this. For example, if I chose a pile diameter of about half a meter, steel pile length of 14 meters, liquefiable length of 14 meters, EI of 50, and plastic movement capacity of let's say 160. I can then make plots between the crustal force I expect and the axial force, and it kind of tells me the limiting envelope. So if I have more crustal force, that means I can have only less amount of axial force. Make sense? So I'm eating more of my capacity in horizontal forces. You can also say what this if I work out, so the instability points are all uh, on the top end. Now, if I plot the same thing with deflection, then I can make this graph the other way, which is what will be the limiting crustal force I can have. Maybe I'll design the pile cap and put around it some foam so that the crust can move and won't hit my pile cap. So that way I can reduce my crustal force and increase my uh, axial force my pile has to carry. And this one is also similar, but getting close to Euler law. For example, if P is zero, axial force is not there, you've got plenty of height on this. Whereas the more closer I'm getting, this is 0.2 and zero point 0.4, you see your curves are coming down. So you can make basically design charts like this for a number of file diameters and so on, which can be used in practice without knowing all the theory, if you like.
Either it change in the curve shape and the type of the point.
At
C graph C. C below.
oh, this one.
Uh,
Oh, this is because you're getting to the buckling limit. So this is the elastic weight, and that's the buckling weight. So that's why it's thinking that. So you haven't got any more to go by. You are on the cusp of yield.
It's like an interaction curve.
Yeah, basically. That's the name for it. I didn't use the name, but yeah. Right. Just to summarize, it's been great fun looking at all these things. Uh, Piles and laterally spreading soils suffer a lot of damage just because of the kinematic loading that's it. And this kinematic loading is coming because of the flowing soil. And they suffer even more if you have this non-liquefiable crust on the top. Because compared to the liquefied soil applying a lateral force on the pile, the non-liquefiable soil can do a lot more, apply a lot bigger forces. Now we've shown this J record is complete, but inadequate for sure by a factor of 2.5 for single piles. But again, as I said, they have upgraded their course to be fair. We then looked at these pile groups in laterally spreading soils, but this time with varying levels of axial loading. And it's important that we consider the combination of axial and lateral load, and that can push the pile towards instability. And you should really be considering this at the design stage of the piles, not after construction of the pile and then when the earthquake happens. So, or like most of what we do with the centrifuge does, we're always in the business of pulling the failed piles out and looking at them. We can afford that because our centrifuges don't cost us millions of dollars to put up the buildings, whereas real buildings do. So you should not ever be in a position where you need to pull out a pile you have driven because the building has collapsed. And this can help you avoid that state. Okay? I think that's it. Any questions? Yeah. Yeah.
How conservative it is to apply the force given by the liquefied load as a uniform time?
Uh, Not that bad actually. We measured those pressures directly, and the limiting value you get is about 20, 25 kPa. And also Tariq Abdun and Dobri, they measure. They also got similar values. So I think uh, it's not zero, but if you are applying 20 kPa on a reasonable sized pile, it's what, say half a meter diameter pile, half times. So it's like 10 kilonewtons per meter, which you can add on. It's not going to be much more than that. So I'm not worried so much. It's actually this thing that dominates the show. Because almost always, if you have, you don't even need uh, the uh, the critical situation is if you have clay layer on the top, you'd expect this as a problem. But where you need to be careful from a design point of view is you got just a sand bed sloping down, and you think it's all going to liquefy. But at the time of the earthquake, the water table is 5 meters below. So you got all this dry sand on the top, which is all going to do exactly like the non-liquefyable crust. So that is the situation I worry about most, because we're not very good at thinking of water table changes. Designers have assumed that, wow, the worst case is always when I have water table on the surface, because then I'll get full liquefaction, therefore it's a problem. But in this case, actually having water table lower causes more trouble. And imagine this is all sand coming at you. Sand can apply so much more passive pressure compared to clay. So you need to be aware of that. Yeah. Okay. So, yeah.
You said you try to apply earthquake load with increasing amplitude. Once the soil liquefies, how you take out the water for the next cycle?
How we?
How you take out the water which is dissipated to the first set of exhalation?
Oh, if you are doing repeat set of earthquakes, it'll all come onto the surface. It'll stay there. It's having a bit of water on the soil surface is not. Um, it does not change your effective stresses, so it's not a problem. We don't need to take the water out ever.
Once one cycle is good, how much time do you wait for the next cycle?
Minimum. I mean, normally to charge up my earthquake actuator, there are other technical things. If you come to Cambridge, I'll show you. It does take time. About 15, 20 minutes. So at prototype scale, that's like having maybe 3, 4 months when you scale it up. Okay, so we know that we dissipated all the flow pressure because we're monitoring that. So we're not worried about that. Any other questions? Okay, good. Lunch at 12:45, right?
Sir, 12:45.
Okay, that's fine. You got some paperwork or coursework?
Tutorials.
What tutorial?
Yeah.
Is it? Ah, he's more of a work master than me.
Building texture amongst the participants.
This is a lot of work.
Starting.